You can point at almost anything in the night sky and feel that given enough time, you could go there. The moon is 3 days away. Mars is a matter of months. These are far places, but they are reachable, and reachable in both directions. Then there is everything else. The first people who leave the solar system for another star will cross a gap so wide that the journey, by the simple arithmetic of distance and speed, runs only one way. They will not be coming home. The nearest star beyond our Sun, Proxima Centauri, lies about 4 light-years off, and our fastest spacecraft would need tens of thousands of years to reach it. Tonight we follow that path outward, to where the solar system truly ends, to why the door behind these travellers quietly closes, and to what it means to leave a home you can never return to. The sun does more than shine, it breathes outward. A steady stream of charged particles leaves its surface at hundreds of kilometres every second, and that stream is called the solar wind. It blows in every direction at once, and it carves a vast bubble in the space around us. Scientists call that bubble the heliosphere, and you can think of it as the sun's true territory, a region kept clear by the constant pressure of its own breath. Inside it, the sun rules. Beyond it lies the space between the stars, filled with the thin gas and dust of the galaxy itself. The edge of that bubble has a name. It is the heliopause, and it marks the place where the solar wind finally loses its push. Out there, the pressure of the wind coming from the sun balances against the pressure of the gas drifting between the stars. Neither side wins. The wind simply stops, the way a river slows and spreads as it meets the still water of a lake. That meeting place is the real boundary of the sun's wind, and it sits far beyond the last planet. To reach it, you travel a long way past Neptune. The heliopause lies around 120 times farther from the sun than the Earth is. We measure that distance in astronomical units, where 1 unit is the gap between the Earth and the sun, about 150 million kilometres. So the edge of the wind sits roughly 120 of those units out. A distance light itself takes about 17 hours to cross. Before you reach the heliopause, you pass through a stranger zone first. Closer in, the solar wind slows down suddenly, dropping below the speed at which disturbances ripple through it. That sudden slowing is called the termination shock, and past it the wind grows hot and turbulent and piles up. The wide, churning region between that shock and the true edge is named the heliosheath. It is a place of slow, hot, tangled plasma, the last layer of the sun's influence before the open galaxy. We know these places are real because 2 machines have crossed them and told us so. Their instruments measured the wind growing quiet, the magnetic field shifting, and the count of galactic particles climbing as the sun's shield fell away behind them. The numbers were not guesses. They arrived as faint radio signals from billions of kilometres away, recorded by antennas on the ground and read by people waiting for them. What waits on the far side is not empty. The space between the stars carries its own thin wind of particles, its own magnetic field, and a steady rain of high-energy cosmic rays that the heliosphere normally holds back. Crossing the heliopause means leaving the calm pocket the sun keeps for us and entering that older, harsher weather of the galaxy. The shield does not end with a wall. It fades, and then it is gone. This is the first edge of any journey to another star. Long before you near another sun, you must pass the place where your own sun stops protecting you. It is quiet there, and dark, and farther than almost anything we picture when we look up. Yet it is only the beginning of the distance ahead. The wind stops, and the real gap to the stars opens beyond it, wider than the bubble we just left. 2 spacecraft have already made this crossing, and they did it almost by accident. Voyager 2 launched first on the 20th of August 1977. Voyager 1 followed about 2 weeks later on the 5th of September. They were built to study the outer planets, not to leave the solar system, yet they were aimed so well that they kept going long after their first work was done. The timing was a rare gift. Once roughly every 176 years, the giant planets line up so a single craft can swing from one to the next, borrowing speed from each. Engineers called the plan the Grand Tour. Voyager 1 visited Jupiter and Saturn. Voyager 2 went further, becoming the only craft ever to fly past Uranus and Neptune, reaching Neptune in 1989. Each flyby bent the path and added speed, flinging both ships outward faster than any rocket alone could have sent them. They carry no solar panels because sunlight grows too weak that far out. Instead, each one runs on the slow heat of decaying plutonium in a device called a radioisotope thermoelectric generator. That heat becomes a trickle of electricity, and it has kept them alive for decades. But the trickle fades a little every year, and one by one the engineers have switched off instruments to save power for the few that still send back useful readings. Voyager 1 is now the most distant object human hands have ever made. It sits more than 24 billion kilometers from the Sun, over 160 astronomical units out, and it climbs farther every second. It moves at about 17 kilometers per second relative to the Sun. Voyager 2 trails behind on a different path, a little slower, having spent some of its speed on those extra worlds. On the 14th of February 1990, Voyager 1 turned its camera back toward home and took one last set of pictures. In one of them, the Earth is a single pale dot, smaller than a single picture element, caught in a band of scattered sunlight. The astronomer Carl Sagan had pushed for that photograph, and the image became known as the pale blue dot. It is the farthest portrait of our world ever taken, a whole planet reduced to a fleck of light. Both craft eventually reached the edge we just described. Voyager 1 crossed the termination shock in late 2004, and Voyager 2 crossed it in 2007. Then Voyager 1 passed the heliopause itself in August 2012, becoming the first human object in interstellar space. Voyager 2 followed in November 2018, and because it carried a working plasma instrument the first had lost, it measured the boundary in even finer detail. Their signals now take more than 20 hours to reach us, travelling at the speed of light. They are gathered by the great dishes of the Deep Space Network, antennas in California, Spain and Australia, listening for a whisper weaker than almost anything else we track. The power that arrives is tiny, far less than the glow of a small bulb. Sometime in the years ahead, the last instruments will likely fall silent as the plutonium gives out. The craft will not stop. They will drift on, cold and dark for millions of years, long after the people who built them are gone. They are the first human things to leave, and they prove the door can be opened. They also show, by their slowness, how far the next one truly is. Even past the heliopause, you have not left the Sun behind. The wind stops there, but gravity reaches much farther. The Sun's pull holds onto objects far beyond the planets and far beyond the edge of the wind, in a vast region most people never picture. That region is the Oort Cloud, and it is the Sun's true gravitational shore. The idea came from a Dutch astronomer named Jan Oort, who proposed it in 1950. He was studying comets, the long-tailed visitors that swing in from the cold and round the Sun and leave again. He noticed that many of them came from enormous distances and from every direction, not just the flat plane where the planets orbit. The simplest explanation was a great spherical shell of icy bodies surrounding the entire solar system, loosely held, ready to be nudged inward now and then. That shell is the Oort Cloud. It is thought to begin somewhere around 2,000 astronomical units from the Sun, and to stretch outward to perhaps 100,000 units, maybe more. Its inner part may be flatter, sometimes called the Hills Cloud, after the astronomer Jack Hills. The outer part is the round shell Oort described. Together they may hold many billions, even trillions of icy bodies, each a frozen mix of ice and rock, most no larger than a mountain. The distances are hard to hold in the mind. At its far edge, the Oort Cloud reaches a meaningful fraction of the way to the next star. Light, which crosses from the Sun to the Earth in about 8 minutes, would need more than a year to reach the outer cloud. The Sun's grip simply fades out there, growing weaker until a passing star or the slow tug of the galaxy can pull a comet free or send one falling inward. We have never seen the Oort Cloud directly. It is too far and too dim. We know it through the comets it sends us. A long-period comet, one that takes thousands or even millions of years to circle the Sun, is a piece of that distant shell knocked loose and falling in. When you see such a comet, you are seeing a traveller from the Sun's farthest country, briefly lit before it returns to the dark. There is one object that may hint at the cloud's inner edge. A small world named Sedna, found in 2003, swings out to nearly 1,000 astronomical units at the far point of its long orbit. It never comes near the planets, and it may belong to that lonely inner region, a frozen marker on the way to the cloud proper. This matters for the journey ahead because it stretches the meaning of the word edge. The planets end at Neptune, around 30 units out. The wind ends at the heliopause, around 120. But the Sun's true reach, the last place its gravity rules, lies far beyond both. Voyager 1, fast as it is, would need roughly 300 years just to reach the inner edge of the Oort Cloud, and tens of thousands of years to pass all the way through it. So when we say the first travellers leave the solar system, we should be honest about what that means. They cross the wind early, but the Sun's gravity follows them for a long, long time. Only when they finally clear the outer cloud are they truly in the open, with no Sun holding them at all. Past that point begins the real emptiness, the gulf that separates one star from the next. Across that emptiness, the nearest light is a faint red star you cannot see with your eyes. Its name is Proxima Centauri, and it lies about 4¼ light years away, the closest known star to our Sun. The word Proxima means nearest, and the name fits. Nothing else we know of is closer. Proxima is part of a small family. It belongs to the Alpha Centauri system, which holds 3 stars bound loosely together. 2 of them, called Alpha Centauri A and Alpha Centauri B, are a close pair, much like our own Sun in size and warmth, circling each other at a comfortable distance. The third Proxima is a small red dwarf far out on the edge of that pair, taking a very long time to loop around them. Together they sit about 4⅓ light years off, in the southern sky, in the constellation Centaurus. Proxima itself is small and cool. It holds only a little more than 1/10 of the Sun's mass, and it burns far dimmer and far redder. Despite that, it was hidden from us until 1915, when the astronomer Robert Innes, working in South Africa, identified it as the nearest star. Its faint light and slow motion had kept it overlooked for centuries, while brighter stars drew the eye. A red dwarf like Proxima has one strange gift. It burns its fuel so slowly that it can shine for trillions of years, far longer than the Sun's expected 10 billion. If you wanted a star that would still be warm in the deep future, a small red one would outlast almost everything else in the sky. But Proxima is also restless. It flares, sending out sudden bursts of radiation that would batter anything orbiting close to it. And something does orbit close. In 2016, astronomers announced a planet circling Proxima, called Proxima b. It is at least a little heavier than the Earth, and it sits in the star's habitable zone, the band where liquid water could in principle exist on a surface. Because Proxima is so cool, that zone lies very near the star, so the planet races around it in just over 11 days. Later work hinted at more worlds, including a possible second planet named Proxima d and a more distant candidate called Proxima c. The habitable zone here is a careful phrase. It means only that the temperature might allow liquid water, not that the place is gentle. Proxima b sits so close to its flaring star that radiation may have stripped much of its air away, and it likely keeps one face turned always toward the star, the way the moon keeps one face toward the Earth. Whether anything could live there is unknown. The honest answer is that we simply do not yet know. Still, this is the destination. When people imagine the first human voyage to another star, this is almost always where they point. It is the nearest possible shore, a real system with real worlds, close enough that we can study its light and wonder about its planets. If a ship ever leaves for another sun, the odds are good that it leaves for this one, and yet nearest is a gentle word for what lies ahead. Proxima is the closest star, and it is still impossibly far. To understand why the journey runs only one way, we have to turn that calm phrase, 4 light years, into a distance the body can feel. That is the next step, and it changes everything. A light year sounds like a measure of time, but it is a measure of distance. It is simply how far light travels in 1 year, and light is the fastest thing there is. To feel what that means, you have to start with how fast light actually moves. Light crosses space at about 300,000 kilometers every second. The exact figure is 299,792 kilometers per second, but 300,000 is close enough to picture. In 1 second, a beam of light could circle the Earth nearly 8 times. Snap your fingers, and in that instant light has already crossed more than 7 times around the whole planet. Now let that speed run for a year. The number it reaches is almost too large to hold. 1 light year is about 9.5 trillion kilometers, or nearly 6 trillion miles. Written out, that is a 9 followed by 12 zeros of kilometers. It is a distance with no everyday handle, because nothing in human life is ever that far from anything else. To get a feel for it, shrink the whole thing down. Imagine the sun reduced to the size of a single grain of sand. On that scale, the Earth would be a speck you could barely see, sitting only a few centimeters away. The nearest star, Proxima, on that same tiny scale, would be another grain of sand resting about 40 kilometers off. A whole day's walk of empty space lies between 2 grains of sand. That gap, almost entirely nothing, is what a few light years really holds. You can also feel it through delay. Light from the sun takes about 8 minutes to reach us, so you always see the sun as it was 8 minutes ago. Light from the moon takes a little over a second, but light from Proxima Centauri takes more than 4 years to arrive. When you look at that star, you see light that left it before some of the words in this sentence were written. The star you see is a memory, 4 years old. That same delay would shape any conversation across the gap. A radio message, which also travels at the speed of light, would take more than 4 years to reach a ship at Proxima, and the reply would take more than 4 years to come back. A single question, and its answer, would eat up the better part of a decade. There is no quick word across that distance, no matter how badly anyone wants one. Between the Sun and Proxima there is almost nothing. No stars, no planets, no way stations, only thin gas, scattered dust, and the faint glow of more distant suns. It is not a road with landmarks. It is a single, uninterrupted gulf, darker and emptier than any desert, and 4.25 light years wide. This is why the abstract number matters. 4 light years can sound almost friendly, a small step compared with the vast galaxy. But unfolded, it is 9.5 trillion kilometers, times 4, of near perfect emptiness. It is a grain of sand, and then 40 kilometers of nothing, and then 1 more grain. Light itself, the fastest thing in the universe, needs over 4 years to make the trip, and nothing we have ever built comes anywhere close to the speed of light. That single fact sets the shape of everything that follows. The distance is fixed, the speed limit is real, and the journey, measured against a human life, becomes something far stranger than far. Hold that distance in mind, and now bring in our fastest machines. The gap between what light can do and what we can do is the heart of the problem. We have built things that move at extraordinary speeds by human standards, and against the distance to a star they are still painfully slow. Start with Voyager 1, the most distant craft we have. It travels at about 17 kilometers per second relative to the Sun. That is roughly 61,000 kilometers per hour, fast enough to cross a continent in a few minutes. It is one of the quickest things we have ever flung outward. Yet at that speed, the trip to Proxima Centauri would take somewhere around 73,000 years. 73,000 years is not a number the body can feel, so anchor it. The whole of recorded human history, from the first written words until now, covers only about 5,000 years. The journey at Voyager's speed would last more than 14 times the length of all written history. Civilizations would rise and fall many times over before the craft arrived, if it were even aimed at Proxima, which it is not. We do have something faster. The Parker Solar Probe, launched in 2018, has become the fastest human-made object ever. As it whips around the Sun at its closest approach, it reaches about 176 kilometers per second, more than 10 times Voyager's speed. But that speed comes from falling deep into the Sun's gravity, like a stone dropping toward a well. The probe is not leaving the solar system. It is circling close to the Sun, borrowing speed that it gives back on the way out. If you could somehow keep that Parker speed and point it at Proxima, the trip would still take more than 7,000 years. Faster, yes, but still far longer than any nation or language has ever lasted. And no craft can actually hold that speed outward, because nothing out there is pushing it along. Once a probe stops accelerating, it simply coasts, and coasting across light years takes ages. New Horizons, the craft that flew past Pluto in 2015, left the Earth faster than any before it, and it now drifts outward at about 16 kilometers per second, a little slower than Voyager 1. It too would need tens of thousands of years to reach the nearest star. These are the quickest things our species has ever made, and every one of them measures the same hard truth. The reason is simple arithmetic. The distance is about 40 trillion kilometers. Our best outbound speed is a few tens of kilometers per second. Divide one by the other, and you get tens of thousands of years. There is no trick hidden in the numbers. The machines are marvels, and the gulf is simply larger than the marvels can cross in any human span. This is why a journey to another star with the engines we have today is not a long trip. It is a trip longer than the species. A child born at launch would die of old age, and so would their grandchildren's grandchildren, thousands of generations deep before the ship ever neared its target. The math alone closes the door on coming back, because by the time you arrived, the Earth you left would be unrecognizable, if it remained at all. To do better, we would need to move not a little faster, but enormously faster, a real fraction of the speed of light. And that brings us straight to the wall that limits every dream of a quick crossing. There is a hard limit on speed built into the universe, and it is the speed of light. Nothing that carries mass can ever reach it. This is not a problem of weak engines or missing fuel. It is a rule woven into how space and time work, and it stands between us and any fast crossing to the stars. The rule came from Albert Einstein in 1905 in his theory of special relativity. Before him, people assumed that if you just kept pushing, you could go faster and faster without end. Einstein showed that the universe does not work that way. The speed of light is a true ceiling, the same for everyone no matter how they move, and matter can approach it but never touch it. The reason lies in what happens as you speed up. The faster an object moves, the harder it becomes to make it move faster still. Its resistance to being pushed, what we call its inertia, climbs without limit as it nears light speed. To reach the speed of light exactly, you would need an infinite push, an endless supply of energy. Since infinite energy does not exist, the goal stays forever out of reach. You can get to 90% of light speed, or 99, or 99.9, but each step closer costs more than the last, and the final step is impossible. This changes the whole shape of the problem. It means there is no engine clever enough, no fuel rich enough, to simply cruise to another star in an afternoon. Even light, which has no mass and moves at the limit, needs more than 4 years to reach Proxima Centauri. Anything we build, carrying mass, must go slower than that. The 4-year figure is not just hard to beat. It cannot be beaten by anything physical at all. So when people imagine a ship flashing to another star in days, they are imagining something the universe forbids. The most we could hope for is to push a craft to a large fraction of light speed, perhaps a 10th, perhaps a 5th, with technology we do not yet have. Even at a 5th of light speed, The trip to Proxima would take more than 20 years, and reaching such a speed at all would demand energies that dwarf anything humanity now commands. There is one strange door that relativity leaves open, and it does not help the people back home. As a ship approaches light speed, time itself slows for those aboard. For them, the journey could feel shorter than it does to anyone watching from Earth. A traveller might experience only a few years while decades pass at home. We will follow that thread carefully later, because it is real and measured. But it bends time only for the travellers, not for the world they leave, and it never lets them outrun light. The speed of light, then, is the wall around every dream of quick travel between stars. It is why the distance to Proxima cannot be shrunk by cleverness, only crossed slowly by mass, or felt strangely by those moving fast enough to bend their own clocks. The wall is firm, and it shapes every honest plan that follows. It does not bend for ambition, and it does not bend for need. Knowing the limit, the question becomes how close we could ever get to it. And there the trouble shifts from physics in the abstract to a brutally practical problem, the simple matter of carrying enough fuel. That problem has a name, and it defeats itself. The deepest trouble with star travel is not speed itself, it is fuel. To go fast, a rocket must throw mass out the back, and the more it wants to speed up, the more fuel it must carry. But that fuel has weight too, and carrying it means carrying still more fuel to push it. The problem feeds on itself, and it has a name. It is the rocket equation. The man who first wrote it down was a Russian schoolteacher named Konstantin Tsiolkovsky in 1903. He worked it out alone, decades before any rocket flew, and it has held true ever since. The equation links three things: how fast you want to go, how fast your engine throws its exhaust, and how much of your ship must be fuel. The cruel part is how those numbers connect. The connection is not gentle and straight, it is exponential. If you want to go a little faster, you need a little more fuel. But if you want to go much faster, the fuel you need does not just grow, it explodes upward. Each extra step of speed demands far more fuel than the step before, because that fuel must also lift and accelerate all the fuel stacked behind it. Beyond a certain point, the tank you would need becomes larger than any ship could be. A simple way to feel it is to picture the fraction of a rocket that is fuel. To reach orbit around the Earth, a rocket is already almost all fuel, with only a small sliver left for the engines, the structure, and the payload. To go to the Moon took the giant Saturn V, a vehicle taller than a 30-story building, almost entirely tanks, to send a small capsule the size of a car. And that was just to the Moon, a 3-day trip. Now aim for a real fraction of light speed. The mass ratio, the comparison between the fully fueled ship and the empty one, grows beyond anything imaginable. With ordinary chemical fuel, the kind that took us to the Moon, reaching even a small fraction of light speed would require more propellant than exists in the entire solar system. The numbers stop being engineering and become a flat impossibility. You would need a tank heavier than planets to push a single ship. This is the trap in the tank. The very thing that makes a rocket go, throwing fuel out the back, becomes the thing that holds it down, because the fuel must carry itself. A chemical rocket simply cannot reach the stars. It runs out of room long before it runs out of dream. The only escape is to change the trade. If your engine could throw its exhaust out far faster, you would need far less of it, and the equation would ease. Chemical fuel throws exhaust at a few kilometers per second. To cross the gulf to a star, you would want an exhaust measured not in a few kilometers per second, but in thousands, or in a real fraction of light speed itself. That means leaving chemistry behind entirely, and that is exactly where the bolder ideas begin. If burning fuel will never be enough, then perhaps you push on sunlight, or ride the force of nuclear blasts, or build a small fusing star inside the ship, or tap the most concentrated fuel the universe allows. Each of these tries to beat the rocket equation in its own way. The first of them needs no fuel aboard at all. It catches a push from light and lets the ship carry almost nothing but itself. One way to escape the fuel trap is to carry no fuel at all. Instead of throwing mass out the back, you let light itself do the pushing. Light carries a tiny amount of momentum, and when it strikes a surface, it gives that surface a gentle shove. Spread a large, thin, mirror-bright sheet in space, and sunlight falling on it becomes a faint but endless push. That sheet is a solar sail. The push from light is real but very small. Sunlight on a sail the size of a few rooms presses about as hard as the weight of a paperclip resting in your hand. You could never feel it. But in space there is nothing to slow you down, so even that faint pressure adds up. Day after day the speed climbs, and unlike a rocket, the sail never runs out of fuel, because the fuel is light, and the light keeps coming. This is not only theory. In 2010, the Japanese Space Agency launched a craft called Icaros, the first to truly sail between planets on sunlight, unfurling a square sheet wider than a tennis court and riding the sun's light toward Venus. In 2019, a small craft called Light Sail 2, built by the Planetary Society, raised its orbit around the Earth using nothing but the pressure of sunlight on its sail. The principle works. We have flown it. But sunlight fades with distance. Far from the sun, a sail gets almost no push, so the sun alone cannot drive a sail to another star. The boldest answer is to stop relying on the sun and build our own light source on the ground. Aim a vast array of lasers at a sail, and you could push it far harder than sunlight ever could, for as long as you kept the beam burning. This is the heart of a project called Breakthrough Starshot, announced in 2016 by the investor Yuri Milner, with the physicist Stephen Hawking among its backers. The idea is daring in its smallness. Instead of a heavy ship, you send a tiny chip, a gram or so, the weight of a few paper clips, attached to a sail only meters wide and thinner than a sheet of paper. A bank of powerful lasers on Earth would hit that sail for a few minutes with enormous power. In those few minutes, the little probe would accelerate to about a fifth of the speed of light. At that pace, it could reach the Alpha Centauri system in roughly 20 years rather than tens of thousands. A handful of grams riding a beam of light, crossing the gulf within a single human lifetime. As the probe flew past Proxima and its neighbours, it would gather what data it could and beam a faint signal home, a message that would itself take over 4 years to arrive. The challenges are immense. The laser array would need more power, focused more precisely than anything we have ever built. The sail must survive that beam without tearing or melting. And the probe, racing at a fifth of light speed, could never slow down. It would flash through the target system in hours, with no way to stop and stay. That last point matters more than it first seems. A sail pushed by light can be flung outward at tremendous speed, but it has no easy way to break at the far end. It arrives only to leave again, gone before it can linger. Which raises a problem that haunts every plan to actually reach another star and remain there. A problem the next ideas must face head-on, with far more violent engines than a sheet of light. If light gives too gentle a push, some engineers reached for the most violent force we know. In the late 1950s, a group of American scientists asked a startling question. What if you drove a spaceship not by burning fuel, but by setting off nuclear bombs behind it? The project was called Orion, and for a few years it was a serious effort, not a fantasy. The plan sounds impossible to say out loud. You build a massive ship with a thick metal plate on its base, called a pusher plate. Behind that plate you drop small nuclear bombs, one after another, and detonate each one a short distance away. Each blast slams against the plate and shoves the ship forward. Great shock absorbers between the plate and the crew soak up the jolt, so the people aboard feel a firm push rather than a killing blow. Then the next bomb drops, and the next, a steady drumbeat of explosions carrying the ship higher and faster. The idea was not the work of cranks. It drew on some of the finest minds of the age. The physicist Freeman Dyson devoted years to it. The bomb designer Ted Taylor helped lead it. The mathematician Stanislaw Ulam, who had worked on the first hydrogen bombs, first sketched the concept. They ran the numbers at General Atomics in California and the numbers were thrilling. A nuclear blast throws its energy out far faster than any chemical flame, which is exactly what the rocket equation begs for. On paper, Orion could do what chemical rockets never could. A single ship might carry not a tiny capsule but thousands of tons, with room for large crews and heavy cargo. Dyson imagined versions that could reach the outer planets in months, and, in their grandest form, even crawl toward the nearest stars over a span of centuries. It was the first design that treated star travel as an engineering problem rather than a daydream. The team even tested the principle, in small and careful ways. They built model craft pushed upward by ordinary chemical explosives to prove that a plate and blast vehicle could fly straight and steady. The little test models leapt into the air and came down under parachutes, and the basic idea held. The motion worked. The plate took the push and passed it on. But Orion carried a shadow it could never shed. To fly from the ground, it would scatter nuclear explosions through the atmosphere, raining radioactive fallout across the sky on its way up. In 1963, the major powers signed the Partial Test Ban Treaty, which forbade nuclear explosions in the atmosphere, in space and underwater. That treaty, signed for good reasons, closed the door on launching Orion from the ground. A ship built and fueled only in deep space might avoid the worst of the fallout, but the cost and the danger kept it on paper. So Project Orion ended, not because the physics failed, but because the method was too dangerous to use near a living world. It remains one of the few Starship ideas that was studied in real detail, with real engineers and real test flights, and then deliberately set aside. Its lesson outlived it. Orion proved that to cross such distances, you must tap energies far beyond chemistry, energies on the scale of the atom itself. The next great design took that lesson and aimed it more precisely, trading crude fission bombs for the cleaner, fiercer fire that powers the stars. It was a plan to build, in effect, a small sun inside the engine and to ride its light to another star. The next serious starship design tried to harness the power of the stars themselves. Stars shine by fusion, the joining of light atomic nuclei into heavier ones, which releases vast amounts of energy. If we could build an engine that fused atoms in a controlled way and threw the result out the back, we would have a drive far more powerful than any chemical rocket, and cleaner than a string of nuclear bombs. That was the dream behind Project Daedalus. Daedalus was the work of the British Interplanetary Society, a group of engineers and scientists who studied the idea through the 1970s. They were not building a ship. They were asking whether a real one could be designed using physics we understood, even if the technology lay decades ahead. The lead figure was an engineer named Alan Bond, and the team worked through every part of the problem in careful detail. Their design was enormous. The full Daedalus ship would weigh many thousands of tons, most of it fuel, and stand taller than a skyscraper. It would burn pellets of fuel in quick bursts, dozens every second, each one crushed and ignited by beams of electrons until it fused and exploded. A strong magnetic field would catch the blast and channel it backward, pushing the ship forward. In a sense, the engine would set off a tiny fusing star many times a second and ride the exhaust. The fuel they chose was unusual. Daedalus would burn a mix of deuterium, a heavy form of hydrogen, and helium-3, a rare light form of helium. Helium-3 is scarce on Earth, so the plan called for mining it from the atmosphere of Jupiter, using floating factories, a piece of the design as ambitious as the ship itself. Everything about Daedalus pushed at the edge of the possible, while staying inside the laws of physics. The performance was staggering on paper. Daedalus was meant to reach about 12% of the speed of light, more than 30,000 kilometers every second. At that pace, it could cross to a nearby star within a single long human lifetime. The team aimed it at Barnard's star, a red dwarf about 6 light-years away, chosen because at the time it was thought to host planets. The trip would take roughly 50 years, but Daedalus had a deliberate limit, and it is the same limit that haunted the light sail. It could not stop. The ship was designed as a flyby, racing through the target system at full speed, gathering data in the brief hours it took to cross, and then continuing on into the dark forever. To slow down would have demanded a second engine and a second mountain of fuel, doubling an already impossible machine. So the designers chose speed over staying, and accepted that their probe would only glance at the star, never arrive in any settled sense. Daedalus was never built, and with the technology of its day it never could be. We still cannot make controlled fusion produce more energy than it consumes, let alone power a starship with it. Yet the study mattered. It showed, line by line, that a fusion starship broke no laws of nature. The obstacles were enormous, but they were obstacles, not walls. A later group revived the effort under the name Project Icarus, refining the same dream with newer knowledge. Fusion remains the most plausible path to the stars that uses energy we can at least name and understand. But there is a fuel even more concentrated than fusion, one that turns matter entirely into energy. It promises the most powerful drive of all, and it is also the hardest thing in the universe to get. There is one fuel more powerful than anything else the universe allows, and it is antimatter. Every kind of particle has a mirror twin with the opposite charge, called its antiparticle. The mirror twin of the electron is the positron. The mirror twin of the proton is the antiproton. When a particle meets its antiparticle, they do not simply collide. They vanish completely, and their entire mass turns into pure energy. This is what makes antimatter so tempting for star travel. In ordinary chemical fuel, only a tiny fraction of the mass becomes energy. Even in nuclear fusion, less than 1% of the fuel's mass converts. But when matter meets antimatter, all of it converts, every gram turned fully into energy, following Einstein's famous link between mass and energy. Gram for gram, antimatter releases far more energy than any other fuel we know by a wide margin. A small amount would carry astonishing power. The energy locked in a single gram of antimatter fully released rivals the output of a large bomb. A starship that could annihilate antimatter and channel the result out the back would have the fiercest drive physics permits, capable in principle of pushing toward a real fraction of light speed without the mountains of fuel that fusion demands. On the page, antimatter is the closest thing to a perfect propellant. The trouble is making it. We can create antimatter, but only in vanishingly small amounts, and only at enormous cost. At laboratories like CERN, the great physics centre near Geneva, scientists produce antiprotons and even build whole antiatoms, but they do it a few particles at a time. All the antimatter humanity has ever made gathered together would amount to far less than a single gram, closer to a few billionths of a gram. To fuel a starship, you would need many grams, perhaps kilograms of the stuff. At current rates and costs, producing even a single gram of antimatter would take far longer than the age of the universe, and cost more than the wealth of the world many times over. It is, by a wide margin, the most expensive substance ever made. The machines that produce it use far more energy to create each particle than that particle could ever give back. For now, antimatter is a fuel we can describe in perfect detail and cannot remotely afford to collect. Storing it is just as hard. Antimatter cannot touch ordinary matter, or it instantly annihilates, so it cannot sit in any normal tank. The only way to hold it is to trap charged antiparticles in a cage of magnetic and electric fields, suspended in a vacuum, never allowed to brush a wall. Such a trap, called a penning trap, can hold a tiny cloud of antiprotons for a time, but scaling that up to store a starship's worth of fuel, safely, for years, is far beyond anything we can do. So antimatter sits in a strange place in this story. It is the most powerful fuel imaginable, the one that would most cleanly beat the rocket equation, and it is also the one furthest out of reach, harder to gather than any other. It marks the upper edge of what physics offers, a perfect engine we cannot build for want of the perfect fuel. And here something easy to overlook comes into view. Every engine we have considered, the sail, the bombs, the fusion star, the antimatter drive, has been measured by how hard it pushes a ship up to speed. But speeding up is only half of any real journey. The other half is stopping, and stopping turns out to be just as hard as leaving. There is a part of star travel that is easy to forget, and it doubles the whole problem. Getting up to speed is only half the journey. At the far end, you have to slow down again. A probe that races to another star at a fifth of light speed and cannot brake will simply tear through the system in a few hours and vanish into the dark beyond. To actually arrive, to stay, you must shed all that speed, and shedding it is as hard as gaining it. This is the half everyone forgets. When people picture reaching another star, they imagine the long acceleration outward and quietly assume the ship glides to a stop at the end. But space offers nothing to push against, and nothing to slow you down. The same emptiness that lets a craft coast for ages without losing speed also means it cannot stop on its own. Whatever speed you build up, you must actively cancel, using just as much effort to brake as you spent to launch. Think of what that means for the engines we have discussed. To reach a fifth of light speed, a fusion ship must burn a staggering amount of fuel. To then slow from that speed back to a near stop, it must burn a second comparable amount, and it must have carried that braking fuel the whole way. But carrying extra fuel makes the ship heavier, which means even more fuel is needed to accelerate it in the first place. The rocket equation strikes twice, once to speed up and once to slow down, and each blow multiplies the other. The Daedalus designers faced this squarely and made a hard choice. Rather than double their already impossible ship, they gave up on stopping entirely and settled for a flyby, a single high-speed glance at the target. The breakthrough Starshot probes make the same surrender. They are flung outward by a ground-based laser, but there is no matching laser at the destination to slow them, so they too can only flash past, never arrive. People have dreamed up ways to brake without carrying braking fuel. One idea is a magnetic sail, a wide loop of magnetic field that drags against the thin gas and particles between the stars, using the destination system's own matter as a brake, the way a parachute uses air. Another is to unfurl a light sail at the far end and let the destination star's light push back against the incoming ship, slowing it as it nears. Both ideas are clever, and both remain untested, paper solutions to a very real wall. The honest picture is stark. Every engine we can imagine struggles to reach a useful fraction of light speed even once. To do it twice, once to leave and once to arrive, pushes the demands far higher still. A flyby is hard. A true arrival, slowing and settling into orbit around another sun, is much harder and may be the single greatest obstacle of all. This is why the first real journey to another star is so often imagined as a one-way trip in the deepest sense. Not only can the travellers not come home, they may struggle even to stop where they're going. The destination, when they reach it, must somehow catch them, or they must somehow shed the speed that carried them across the gulf. And if stopping at the far star is this hard, then consider the full shape of a round trip, out and back, with a stop at each end. That is not twice as hard as a flyby. It is far more than twice, because every stage multiplies the one before, and the demands climb fourfold into the impossible. A round trip to another star is not twice as hard as going one way. It is far worse than that, because the difficulties pile on top of one another. A true journey out and back has 4 separate stages, and each one demands its own enormous effort, stacked atop the last. Lay the stages out plainly. First, you must speed up to leave, accelerating from rest to a real fraction of light speed. Second, at the far star, you must slow down again, braking from that speed to a near stop so you can stay. Third, when it is time to come home, you must speed up once more, accelerating back to cruising speed for the return. And fourth, arriving back at the solar system, you must brake a final time so you do not tear straight through it. 4 full changes of speed, each as demanding as launching a starship from scratch. The cruelty is in how these stages combine. The rocket equation does not add them, it multiplies them. The fuel for the final braking must be carried through all 3 earlier stages, which means you must accelerate it, decelerate it, and accelerate it again before you ever use it. The fuel for the return trip must be hauled all the way to the far star and back up to speed before it does any work. Each stage must carry the fuel for every stage that follows, and since the fuel needed grows exponentially with speed, the totals climb beyond all reason. A simple way to feel it is to imagine the ship as a set of nested shells, each one a smaller ship riding inside a larger tank. The innermost shell is what finally lands back home. Around it is the fuel to break at Earth. Around that, the fuel to leave the far star. Around that, the fuel to break at the far star. And around all of it, the fuel to leave Earth in the first place. Each layer must lift everything inside it, and the outermost layer becomes monstrous, dwarfing the tiny capsule at the centre that actually completes the trip. For chemical or even fusion engines, the numbers for a round trip pass from merely impossible into the absurd. If a one-way flyby already strains every limit we know, a stop-and-return mission multiplies those strains until the required fuel could outweigh small worlds. There is no quiet trick that softens this. It is built into the mathematics of throwing mass to move. This is the deepest reason the first journey runs one way. It is not only that the travellers would be gone for longer than a lifetime, it is that the physics of stopping and returning is so much harsher than the physics of simply going, that a return is a different order of impossible. To leave is hard. To leave, stop, turn around, come back, and stop again is hard 4 times over, each hardness feeding the next. So when we picture the first humans crossing to another star, we should picture a path that bends only outward. They might reach a new sun. They will almost certainly never bring themselves back across that gulf to the old one. The door behind them does not slam. It is simply that the way back asks 4 times the impossible thing the way out already asked. And yet, strangely, the universe offers the travellers one gift in exchange, a gift hidden inside the very speeds that make return so hard. When you move fast enough, close to the speed of light, time itself begins to bend. The clock aboard the ship runs slow. For the traveller, the long journey shrinks, even as the world they left races ahead. That bending of time is real, and it changes what the word journey even means. Something strange happens to time when you move very fast. It slows down, not in feeling, but in fact. A clock racing across space at near the speed of light ticks more slowly than a clock standing still, and this is not an illusion or a trick of perception. It is how the universe is built, and it has been measured countless times. The effect comes from the same theory that set the speed limit, Einstein's special relativity, from 1905. One of its deepest results is that time is not the same for everyone. How fast your clock runs depends on how fast you're moving. At everyday speeds, the difference is far too small to notice, but as you approach the speed of light, it grows large, and then enormous. At low speeds, the slowing is tiny. A passenger on a fast aircraft ages a few billionths of a second less than someone on the ground over a long flight, far too little to feel. But the effect climbs steeply as you near light speed. At half the speed of light, clocks run noticeably slow. At 90%, time aboard runs at less than half the rate it does at home. Push closer still to light speed, and the traveller's clock can crawl while the outside world races on. We know this is real because we have watched it happen. Tiny particles called muons, made high in the atmosphere by cosmic rays, should decay almost instantly, far too fast to reach the ground. Yet because they fall toward us at nearly the speed of light, their internal clocks run slow, and they survive long enough to be detected at the surface in large numbers. Precise atomic clocks flown on aircraft and carried on satellites show the same thing, ticking measurably slower than their twins left on the ground. For a starship, this changes the meaning of the journey. Imagine a ship that could somehow travel at a high fraction of light speed toward a star many light years away. To everyone watching from Earth, the trip still takes many years, because no ship can outrun light. But to the travellers aboard, moving so fast that their own clocks crawl, far less time would pass. A voyage that takes decades as seen from home might feel like only a handful of years to those making it. The faster the ship, the stronger the effect. Close enough to light speed, in principle, a crew might cross great stretches of the galaxy within their own lifetimes, even though tens of thousands of years would pass outside. Their bodies would age only a little, their clocks barely advancing while the universe around them swept forward. The distance does not shrink for them so much as their experience of time compresses. It is important to be honest about how far this lies from reach. To gain a strong slowing of time, you must travel at a real fraction of light speed, and we have already seen how brutally hard that is to achieve. Our fastest craft move at far less than 1% of light speed, where time dilation is utterly negligible. The gift is real, but it's locked behind the same wall of energy that guards every fast crossing. Still, the effect reshapes what a one-way journey could be. The travellers do not simply vanish into a long sleep of centuries. If they moved fast enough, they would live the trip as a short span of years, arriving still young at a star the rest of us would not live to see them reach. But the same motion that spares them spends the world behind them, and that split between two clocks creates one of the strangest situations in all of physics, the case of the twin who stays home. Picture two twins. One boards a starship and races toward a distant sun at near the speed of light. The other stays home on Earth. Because the travelling twin moves so fast, their clock runs slow, and they age more slowly than the twin who stayed. When the traveller finally returns, they are younger than the sibling they left behind. This is the twin puzzle, and it is true. At first, it sounds like a riddle with no answer. If motion is relative, you might ask, why does the travelling twin age less rather than the one at home? From the traveller's point of view, isn't it the Earth that rushed away and came back? The reason the situation is not even-handed is the turning around. The twin who leaves must speed up, slow down, reverse, and return, feeling real forces of acceleration. The twin at home never does. That difference breaks the tie, and it is the traveller whose clock falls behind. We can put rough numbers to it. Suppose a ship could travel at 90% of the speed of light to a star about 4 light-years away and come straight back. To the twin on Earth, the round trip takes a little under 10 years, since the ship moves only a bit slower than light across 8 light-years of distance. But to the twin aboard, whose clock runs slow the whole way, only about 4 years pass. They step off the ship 4 years older, into a world that has aged nearly 10. Push the speed higher, and the gap widens dramatically. At 99% of light speed, the traveller's clock runs about 7 times slower than home. A trip that takes 70 years as seen from Earth would feel like only 10 years to the crew. They would return after a decade of their own lives to find 70 years gone on Earth, their friends old or buried, their world changed past recognizing. The closer to light speed, the more violently the two clocks diverge. This is not a thought experiment without evidence. We have flown precise atomic clocks around the world on aircraft and compared them with identical clocks left behind, and the travelling clocks came back having ticked a little less, exactly as the theory predicts. The effect on an airplane is measured in billionths of a second, but it is real and repeatable. Scaled up to near light speed, those billionths would become years. For the first travellers to another star, the twin puzzle stops being a riddle and becomes their life. Anyone they leave behind ages at the normal rate. If the ship moves fast enough for time dilation to matter, the travellers will return, if they could return at all, to find everyone they knew, far older or long dead. And since we have seen that returning is itself nearly impossible, the more likely truth is that they never come back to settle the comparison at all. They simply age slowly in their small moving world, while everything they left grows old without them. There is a quiet grief in this. The traveller does not feel time slow. Aboard the ship, every day is an ordinary day, clocks ticking normally, hearts beating at their usual pace. The slowing is only ever seen from outside in the mismatch between the two lives. The travellers live their years fully and naturally. It is the comparison with home that reveals the gap, a gap that grows with every kilometre of speed. So the same physics that might let a crew survive a journey of light years also guarantees that the home they remember will not survive the wait. While the traveller holds on to a few short years, the Earth they left does not stand still. It runs ahead, faster and farther, into a future the traveller can never share. While the travellers hold on to their slow short years, the Earth they left behind runs ahead without them. This is the other face of time dilation, and it may be the loneliest part of the whole journey. The crew does not simply lose contact with home. They lose the home itself to the rush of time, watching, if they could watch, generations rise and pass while only a few years cross their own lives. Consider what this means for a fast voyage. Suppose a ship crosses to a star and the crew experiences only 10 years, while 100 years pass on Earth. During that single decade aboard, an entire century unfolds at home. Children are born, grow old, and die. Leaders come and go, whole ways of living change. The travellers step away for what feels like a long but ordinary stretch of their lives, and the world they knew slides 100 years into its future while their backs are turned. The faster the ship, the wider this gulf grows. At speeds very close to light, a crew might age only a few years while thousands pass on Earth. They could leave a familiar world and, in their own brief experience, arrive at a star to find that back home, the languages they spoke have faded, the nations they knew have dissolved, and even the shape of human life has moved beyond anything they would recognise. They would be, in a real sense, refugees from a vanished time, carrying a world inside them that no longer exists outside. This is more than the ordinary distance of any long voyage. Sailors of the past who crossed oceans returned to the same world they had left, only a little older. They could pick up the thread of their lives, but a fast relativistic traveller cannot. Even if, against all odds, they came home, they would arrive not into their own era but into a distant future, strangers to everyone, their friends and family long gone to history. Home as they knew it would not be a place they could return to. It would be a story in old records. There is a strange beauty tangled with the loss. A crew moving fast enough is, in effect, travelling forward in time. They are seeing the future of the human world, skipping over the slow centuries between. If they could somehow look back at Earth and survive to read its history, they would find ages compressed into their short trip. The long unfolding of events squeezed into a single watch aboard ship. They become time travellers of a sort, carried forward by sheer speed, unable ever to go back. But for the people left on Earth, the picture is gentler and sadder. They watch the ship recede and know that those aboard are aging slowly, frozen almost young against the racing years at home. A mother might launch a child into the dark and understand that she will be long dead before that child has aged even a little. The bond is not broken by anger or distance, but by time running at two different speeds, pulling the two lives apart faster than any ocean ever could. This is why the journey to another star is a true farewell, deeper than any goodbye on Earth. It is not only that the travellers cannot return across the gulf of space, it is that even time itself conspires to separate them, letting the world they love run ahead into a future they can never rejoin. The door behind them closes not only in distance but in years, and so far we have imagined ships fast enough to bend time. But the more likely first journeys will be slow, far slower than light, taking not years but centuries. For those there is no gift of slowed time. There is only the long, patient passage of generations in a small world sealed against the dark, carrying its people across the gulf one lifetime at a time. If you cannot move fast enough to bend time, then you must build a world that can hold its people across centuries. This is the idea of the generation ship. It is a vessel so large and so complete that the crew can live their whole lives aboard, have children, grow old, and die, while the ship carries on toward a star their descendants will reach. No one who boards it at launch will ever step onto the new world. The journey belongs to people not yet born. The name says it plainly. A generation ship carries not one crew but many, each generation passing the voyage to the next. like a relay run across hundreds of years. The first travellers begin the trip. Their grandchildren live their entire lives in the middle of it, knowing only the ship. Their distant descendants, many generations on, are the ones who finally arrive. The ship is less a vehicle than a small moving homeland. To make this possible, the ship must be a closed world, sealed against the dark. It must carry its own air to breathe, its own water to drink, and its own way to grow food, with no harbour to resupply along the way. It must hold everything its people need for centuries, recycling almost every atom because nothing new can be brought aboard once it leaves. In effect, it must be a tiny Earth, complete in itself, sailing through the emptiness between stars. The size such a ship would need is hard to imagine. To carry enough people, enough farmland, enough water and air for hundreds of years, it might have to be many kilometres long, a structure more like a small city or a hollowed mountain than a rocket. Some designs imagine spinning the whole vessel slowly, so that the spin presses people gently outward against the inner walls and gives them a kind of artificial gravity, a floor to stand on and a sky curving overhead. That curving sky is the heart of the idea. The people inside would live on the inner surface of a great rotating cylinder, with their ground curving up and around them, and the far fields hanging overhead like an inverted landscape. Lamps would stand in for the sun, brightening and dimming to mark day and night. Soil, plants, perhaps small animals, would all have to be carried along and kept alive, a whole working ecosystem folded into a metal shell. The engineering is daunting, but the deeper challenge is that the ship must never fail in any way that matters, not once, across centuries. A pump that breaks, a crop that dies, a leak that drains the air, any of these could doom everyone aboard, with no rescue possible and no shorter reach. The margin for error is thinner than on any voyage humans have ever made, because the voyage is longer than any nation has ever lasted, and there is nowhere to turn back to. And yet the generation ship remains, for now, the most realistic way we can picture actually crossing to another star with people aboard. It asks no new physics, no antimatter we cannot make, no engine we cannot build. It asks instead for patience on a scale we have never tried, and for a society that can hold itself together in a sealed world for longer than memory. Which raises a question that has nothing to do with engines or fuel. Long before the ship arrives, children will be born inside it, into a journey they never chose, who will live and die having never seen the sky we leave behind. On a generation ship, most of the travellers never choose to go. They are born into the journey. The people who board at launch make a choice, however hard, to leave Earth behind. But their children do not. Their grandchildren do not. The crew who finally arrives at the new star, many generations later, never agreed to anything. They simply opened their eyes inside a moving world and found that the voyage was already their whole life. This is one of the strangest features of the generation ship, and one of the most troubling. A child born in the middle of such a trip will live their entire life in a sealed vessel between the stars. They will never walk on the Earth their ancestors left. They will never set foot on the world their descendants will reach. The ship is the only home they will ever know, from first breath to last, and they had no say in being placed there. Think about what such a life would hold. A child aboard would grow up knowing the curving walls, the artificial day and night, the same faces and corridors year after year. The wider universe would be something seen on screens and through small windows, a black field of distant stars with no destination close enough to touch. Earth would be a place in stories and records, a blue world they came from but can never visit. The new star would be a promise meant for people not yet born. This raises hard questions that no engine can answer. Is it right to commit children, and their children, to a life they did not choose, in a place they cannot leave? Those who plan such voyages must decide whether it is fair to bind whole generations to a mission begun by their ancestors. The first crew accepts the journey for themselves, but they also accept it on behalf of everyone who will be born along the way, deciding the shape of lives that do not yet exist. There is a gentler way to see it, though. In truth, none of us chose to be born where we were, or when. A child born on Earth did not choose this planet, this century, this country, or this family. We all arrive in the middle of a story already in motion, and we make our lives from where we find ourselves. A child on a generation ship would be doing the same thing, only their world would be smaller and stranger, a vessel rather than a planet. Still, the ship's world is narrower than any on Earth, and the stakes are higher. A society sealed in a small space for centuries must teach each new generation not only how to live, but how to keep the ship running, how to grow the food, mend the machines, and hold the peace. The knowledge that keeps everyone alive must pass unbroken from parent to child, generation after generation, with no room to forget. A single lost skill, a single broken thread of teaching could put everyone in danger. And there is a quieter risk, of the heart rather than the machinery. Later generations might come to resent the voyage, feeling trapped by a choice their ancestors made. Or they might forget why they are travelling at all, losing the sense of purpose that launched the ship until the journey becomes merely the way things are. To hold a mission together across centuries, a people must carry not just tools and seeds, but meaning, handed down intact. All of this depends on something simpler and more fragile still, the closed world that keeps them breathing, drinking and eating, with nothing coming in from outside. A generation ship has no harbour and no resupply. Whatever it needs for the whole journey, it must carry from the start or make and remake along the way. This is the closed garden, a vessel that must recycle nearly everything, turning waste back into food, foul air back into clean, used water back into drink, around and around for centuries. Nothing can be thrown away, because there is nowhere to throw it, and nothing new can be brought in. Start with air. People breathe in oxygen and breathe out carbon dioxide, and on Earth the plants quietly reverse that exchange, taking in the carbon dioxide and giving back oxygen. A starship must run that same cycle inside its walls, with no outside forest to lean on. It would likely use vast banks of living plants or algae, lit by lamps, to drink the crew's exhaled breath and return the oxygen they need. The green of the ship is not decoration. It is the lungs of the whole world. Water is the same story told again. Every drop must be used and reused without end. The water people drink leaves their bodies as sweat and waste, and all of it must be captured, cleaned, and made fit to drink once more. There is no river to draw from and no rain to wait for. A starship would purify its water in tight loops, the same molecules passing through the crew and the machines and back again, year after year, with losses kept as close to zero as the engineers can manage. Food is the hardest loop of all, because people must eat every day, and food cannot simply be stored for centuries. The ship would have to grow its own, farming inside its hull, raising crops under artificial light in carefully tended soil or in tanks of nutrient-rich water. The waste from the crew would feed the soil that feeds the crops that feed the crew. It is a tight circle and every link must hold. A blight that kills a harvest, on Earth, is a hardship. On a starship with no other source, it could be the end. We have practiced this on a small scale and learned how hard it is. On the International Space Station, astronauts already recycle much of their water and some of their air, reclaiming moisture from breath and sweat and even urine, turning it back into drinking water. It works, but it takes constant care and constant repair. The station is also resupplied often from Earth, which a starship could never be. The closed loop on a true generation ship would have to be far tighter and far more reliable than anything we have yet built. There was also a bold experiment on the ground in the Arizona desert called Biosphere 2. In the early 1990s, a small group of people sealed themselves inside a giant glass enclosure, trying to live entirely off its recycled air, water and crops. They learned how delicate such a system is. The oxygen inside slowly fell, crops struggled, and the balance proved harder to hold than anyone expected. It was a humbling lesson in how much a living world quietly does for us, and how hard it is to copy. The closed garden, then, is not a minor detail of star travel. It may be the single hardest part of keeping people alive across the Gulf. The engines get the ship moving, but the garden keeps the people breathing, drinking and eating every single day for longer than any harvest on Earth has ever had to last unbroken. And even a perfect garden cannot shield the crew from one thing that pours through the walls from outside, unseen and unending, all the way across the dark. The space between the stars is not truly empty, and what fills it is dangerous. Pouring through it, in every direction, is a thin, ceaseless rain of high-energy particles called cosmic radiation. These are not raindrops, but atomic fragments, mostly the bare cores of atoms, flung outward by exploding stars and other violent events across the galaxy, travelling at nearly the speed of light. They pass through space, through metal, and through flesh, and they never stop. On Earth, we barely notice them. Our planet wraps us in two great shields. The first is Earth's magnetic field, a vast invisible cocoon that deflects many of these particles before they ever arrive. The second is the thick blanket of our atmosphere, which absorbs most of what gets through. Together they soak up the cosmic rain so thoroughly that, standing on the ground, you receive only a faint trickle of it, harmless in ordinary life. The sun adds a third shield, the very bubble we crossed at the start of this journey. The heliosphere, blown out by the solar wind, pushes back against much of the galaxy's radiation, holding a good share of it at bay throughout the solar system. But beyond the heliopause, in true interstellar space, that shield is gone. A starship crossing the Gulf would sail through the full, unfiltered rain, with none of the protections that keep us safe at home. What this radiation does to the body is the heart of the danger. When these fast particles strike living tissue, they tear through cells and break the delicate strands of genetic material inside them. A heavy dose can cause radiation sickness quickly. A steady lower dose over years raises the risk of cancer and can damage the nervous system and the brain. For a crew exposed for decades, with no break and no shelter of atmosphere, the threat is constant and cumulative, building with every passing year. There is a second source of danger closer to any star, including our own and the one ahead. Stars throw out sudden storms of particles in solar flares and great eruptions of their outer layers. A single strong storm can deliver in hours a dose that would take years to gather from the background rain. A ship near the start or end of its trip, close to a flaring star like Proxima, would have to weather these bursts, which arrive with little warning and great force. Shielding against all this is heavy and hard. The simplest protection is mass, putting thick walls of material between the crew and the outside, the way the atmosphere protects us. Water makes a good shield, and a ship might wrap its living quarters in tanks of it, doubling its drinking supply as armour. But shielding adds weight, and weight, as we have seen, is the enemy of every star voyage. Each ton of shielding is a ton that must be accelerated and somehow slowed. Some designs imagine giving the ship its own magnetic field, a small artificial version of Earth's cocoon, to push the charged particles aside without the weight of solid walls. The idea is sound in principle, since the particles carry charge and magnets deflect charge. But generating a field strong enough and wide enough to wrap a whole ship, and powering it for centuries, is far beyond anything we can do today. It remains a hope rather than a plan. The invisible rain, then, is one more reason the journey is so unforgiving. The crew would need to hide from a sky that never lets up year upon year, and even sheltered from radiation, their bodies would face another slow harm, one that comes not from outside but from the simple, lasting absence of the ground's pull. Take away gravity, and the human body begins to come apart slowly and quietly. We are built for the steady pull of the Earth, and when that pull is gone, the body, sensing it no longer needs to fight, starts letting go of the very strength that kept us upright. A long voyage in weightlessness is not restful. It is a slow unbuilding of the body system by system over months and years. The bones go first and most noticeably. On Earth, Your skeleton works constantly against gravity, and that effort keeps it dense and strong. In weightlessness, the bones are no longer loaded, and the body begins to dissolve them, leaching away the minerals that make them hard. Astronauts on the space station lose bone at a rate of more than 1% a month in some places, far faster than the thinning of old age on Earth. Over years, unchecked, this would leave the skeleton dangerously weak. The muscles fade alongside the bones. Without weight to lift or a floor to push against, muscles waste away, especially the large ones of the legs and back that hold us up against gravity. The heart, which is itself a muscle, has an easier job when blood no longer has to be pumped upward against the Earth's pull, and it too can weaken over time. Astronauts fight this with hours of daily exercise, strapped into machines that mimic the loads of Earth, and even then they return home weakened. Fluids shift as well in ways that surprise. On Earth, gravity pulls the body's fluids gently downward, pooling them in the legs. In weightlessness, those fluids drift upward instead, swelling the face and pressing in the head. Astronauts arrive in orbit with puffy faces and stuffed sinuses, as if holding a constant mild cold. More worryingly, this upward shift presses on the eyes, and many astronauts find their vision changed after long missions, some of it not fully recovered on return. There is a clear answer to all of this, and it is the same spin we met in the Generation ship. If the vessel rotates, the crew is pressed against its inner walls, and that pressure stands in for gravity, giving the bones a load to bear and the muscles a weight to lift. A large enough spinning ship could hold its people at something close to Earth's pull, sparing them the slow unbuilding of weightlessness. This is why so many serious starship designs are built as great turning wheels or cylinders. But spin is not free or simple. To feel like Earth's gravity, a ship must either be very large and turn slowly or smaller and turn fast. Spin a small ship quickly, and the difference in pull between your head and your feet becomes noticeable, and the motion can unsettle the inner ear, leaving people dizzy and sick. To give smooth, comfortable, Earth-like weight, the rotating part must be big, hundreds of meters across, which drives up the size and mass of the whole vessel. We know all of this because we have lived it, in low orbit, for decades. The space station has taught us, in real bodies, exactly how weightlessness erodes us, and exactly how hard it is to hold that erosion back. Every lesson points the same way. For a voyage of centuries, the crew cannot simply float. They must carry a piece of Earth's pull with them, spun into the structure of their world, or arrive at the new star as a people too frail to stand. And a frail body is only one threat to the crew. There is also the question of how few people can safely make such a journey at all, and still arrive healthy generations later. How many people do you need to start a new branch of humanity at another star? The question sounds strange, but for a Generation ship it is one of the most important of all. Too few travellers, and their descendants, marrying only among themselves for generations, would grow sickly and weak. The crew must be large enough to stay healthy across all the centuries of the trip, a smallest possible village carried between the stars. The danger of too few comes down to the way we inherit traits. Every person carries some hidden flaws in their genes, harmless when paired with a healthy version from the other parent. In a large population, those flaws stay rare and mostly hidden, but in a tiny closed group where everyone is related, the same flaws turn up on both sides far more often, and they begin to show as disease and weakness. Breeders have long known this danger in animals, and it is just as real in people. So the planners of a Generation ship must ask how large a crew avoids this trap. The answer is not obvious, and estimates have changed as the science has sharpened. Early guesses suggested that a few tens of people might be enough to start with. But more careful studies, looking at how genetic variety thins over many generations, have pushed the number far higher, into the hundreds, and by some careful estimates into the thousands, to keep a population robust across a long voyage. One often cited study put the safe minimum at several thousand people, with around 10,000 giving a comfortable margin, in order to preserve enough genetic variety for the long haul. With that many travellers, the hidden flaws stay diluted. Rare versions of genes are not lost by chance, and the population can absorb the slow drift of the generations without sliding into weakness. Fewer than that, and the risk climbs that the arriving crew would be less healthy than the one that set out. There are ways to shrink the number, but each adds its own weight of difficulty. A ship might carry not thousands of living people, but a great bank of frozen genetic material, stored eggs and sperm or seeds of human variety, to refresh the gene pool along the way without carrying the bodies. A smaller living crew could then draw on that stored variety to keep their children healthy. It is a clever trade. Fewer mouths to feed in exchange for a delicate library that must survive centuries intact. The planners must also think about balance and time. The crew needs a healthy spread of ages, so that there are always people able to work, to teach, and to raise the next generation, with no gap where the skills or the births fall away. The population must be managed with care, neither growing too large for the ship's closed garden to feed, nor shrinking so far that it loses its variety and its strength. It is a slow, deliberate kind of stewardship, planning births across centuries. All of this makes the smallest village a careful piece of engineering in its own right, as real as the engines and the shielding. The ship is not just a machine, but a population, and that population must be designed to last. Get the number wrong, too few, and the people who arrive at the new star may be too frail and too few to build anything there at all. The whole long voyage undone by arithmetic of blood. Yet even a large, healthy crew faces a harm that no number can cure, a weight that presses not on the body but on the mind, across the long dark of the years. There is a kind of distance on a starship that no engine can shorten, the distance inside the mind. A crew sealed in a small world, far from everything familiar, for years or for whole lifetimes, faces a quieter danger than radiation or weightlessness. It is the strain of isolation, of the same walls and the same faces and the endless dark outside, pressing on the human spirit through the long quiet of the voyage. We are social creatures, shaped by wide horizons and many companions. On a long voyage, both are taken away. The crew would see only the people aboard, perhaps a few hundred or a few thousand at most, the same individuals for the rest of their lives. There would be no new friends from outside, no strangers, no crowds, no escape from any quarrel or grief. The social world would be fixed and small, and every relationship within it would have to last for better or worse across decades. Outside the walls there would be nothing to break the sameness. No weather, no seasons in the true sense, no cities passing by, only the unchanging black of space and the distant fixed points of the stars. Day and night would be set by lamps on a schedule, not by a real sun. The mind, which feeds on novelty and change, would have to live for years on a diet of repetition, in a world where almost nothing new ever happens outside what the people make for themselves. We have early glimpses of what this does to people. On long stays aboard the space station, in remote research bases in Antarctica through the dark winter, and in sealed experiments built to mimic voyages to Mars, people have shown the strain. There can be low moods and irritability, trouble sleeping, friction between crewmates, and a slow wearing down of morale over the months. These are short trials, lasting a year or two at most. A starship voyage would last beyond any of them by far. The deepest version of this strain belongs to the middle generations of a true generation ship. The first crew at least remembers Earth, and the last will see the new world. But those born and dying in the long middle will know only the ship, with neither a remembered home behind them, nor a destination ahead within their reach. Their whole lives would pass in transit, in a world that is only ever on its way. To live a full life with meaning, in that in-between, is a challenge no explorer before has faced. To carry people through this, a starship would need to be more than a machine that keeps bodies alive. It would need to keep minds and spirits alive too. That means space to move and be alone, beauty to rest the eyes, work that matters, and ways to mark time and find purpose. It means art, ritual, celebration, and play. The soft things that hold a people together. A society that forgets these might keep breathing and still come apart, its bonds fraying in the long quiet. So the success of such a voyage may rest as much on the heart as on the engine. A ship can have perfect air and water and food, flawless shielding and gentle spin, and still fail if its people lose hope, or turn on one another, or simply cannot bear the years. The mind is fragile in its own way, and the dark is very long. To cross it, a people must carry not only their bodies, but their reasons to keep going. And one of the things that wears most on the mind is the slow fading of every voice from home, growing fainter and slower the farther the ship sails. Every word from home takes longer to arrive the farther you go, until conversation itself becomes impossible. This is the fading voice, the slow stretching of every message across a widening gulf. A radio signal, the fastest way we have to speak across space, still travels only at the speed of light, and against the distance between stars, even light is slow. The farther the ship sails, the longer each word takes to reach it, and the longer the answer takes to come back. Near home, we already feel a small taste of this. A signal to the moon takes a little over a second each way, enough to make conversation a touch awkward, with a short pause after every sentence. To Mars, depending on where the planets sit, a message takes from several minutes to around 20 minutes one way. A simple question and its answer can take the better part of an hour. There is no real conversation with Mars, only messages left and answered, like letters sent at the speed of light. Now stretch that to the stars, and the gap becomes a chasm. A ship at Proxima Centauri would be more than 4 light-years away, so a message would take over 4 years to arrive and the reply over 4 years to return. A single round of question and answer would eat up more than 8 years. By the time you heard back, the child who sent the question might be grown. Conversation, in any normal sense, simply ends. What remains is a slow exchange of messages across the better part of a decade. For the travellers, this means a gradual, irreversible cutting of the cord. As the ship pulls away, the delay grows month by month, and the back and forth of talk stretches into longer and longer silences. First, the easy chat becomes slow. Then it becomes a matter of years. At last the gap is so wide that no real exchange is possible at all, and home becomes a voice that speaks only in long, one-sided messages, arriving from a past that recedes further with every passing year. There is a strange doubling in this, because the news from home is always old. A message that arrives after 4 years tells you what was true 4 years ago. The people who sent it have moved on, aged, perhaps passed away, while their words were still crossing the dark. The travellers would live always behind the present of Earth, hearing of events long after they happened, unable ever to respond in time. Home would become a kind of history that keeps unfolding, always out of reach, always already past, and it grows only worse with distance. A generation ship crawling along far slower than light, taking centuries to cross, would draw out the delay without end. Late in such a voyage, a message to Earth and its reply might take many years, then decades. The practical truth is that, fairly early on, the ship would fall out of any living contact with home and would have to rely entirely on itself, carrying every answer it might ever need inside its own walls, because none could arrive from outside in time to help. This is part of what makes the journey a true departure, and not merely a long trip. The travellers do not just leave a place. They leave the conversation of humanity, the shared present we all live in. They slip out of the ongoing now of Earth into a separate, lonelier time of their own, where every voice from home arrives faint, slow, and already old. Faced with such a long and lonely passage, some have asked whether the travellers must be awake for it at all, or whether they might sleep through the dark. What if the travellers did not have to live through the long voyage awake? What if they could sleep through it, their bodies slowed almost to stillness, and wake at the far star having barely aged? This is the dream of hibernation, of suspended animation, a way to skip the decades of darkness rather than endure them. It would solve at a stroke many of the hardest problems of star travel, if only it could be done. The appeal is enormous. A sleeping crew breathes slowly, eats little or nothing, and does not suffer the boredom and strain of the long quiet. They would need far less food and water and air, lightening the ship's closed garden. They would not grow restless or lonely, would not quarrel across the years, would not have to fill empty decades with meaning. They might simply close their eyes near Earth and open them near another sun, the long crossing passing for them in what feels like a single night. Nature hints that something like this is possible. Many animals already do a version of it. Bears, ground squirrels and other creatures pass the cold months in hibernation, their body temperature dropping, their heartbeat and breathing slowing to a crawl, their need for food nearly vanishing. Some frogs can freeze almost solid through winter and thaw alive in spring. These animals show that a body can be slowed far down and brought back, that deep rest is not the same as death, and that life can pause and resume. Humans do not naturally hibernate, but medicine has found small footholds in that direction. Doctors sometimes cool patients deliberately, lowering body temperature during certain surgeries or after cardiac arrest, to slow the body's processes and protect the brain when blood flow is reduced. This careful, controlled cooling buys precious time and shows that a human body can be slowed and safely warmed again. It is a faint, real echo of true hibernation, practiced now in hospitals. Space agencies have taken the idea seriously enough to study it. Researchers have looked at whether astronauts on long trips to Mars and beyond might be placed in a light hibernation, cooled and sedated for weeks at a time in rotating shifts. Such studies are early and cautious, but they treat suspended sleep not as fantasy, but as a problem to be worked on, a tool that might one day make long voyages easier on both the body and the supplies. The obstacles, though, are real and large. We do not yet know how to safely hold a human in deep suspension for years, let alone for the centuries a slow starship would take. Long stillness brings its own harms, the same wasting of muscle and bone that weightlessness causes, the risk of clots and bed sores, the slow decay of a body that does not move. To truly pause a person for decades and revive them whole is far beyond our reach, however promising the early signs. For a crewed voyage that lasts longer than a life, hibernation may be the only way a single set of travellers could ever survive to arrive, rather than handing the journey down through generations. If it could be perfected, the first humans to reach another star might be the very ones who left, asleep through the centuries, waking as strangers in a new sky. Without it, the trip belongs to descendants who never knew the start. Whether they sleep or wake, though, there comes a moment on any such voyage that cannot be undone, a threshold past which home is no longer a place they could ever reach again. On any journey this long, there comes a moment when home stops being a destination and becomes only a memory. It is the point of no return, the threshold past which the travellers could never get back to Earth even if they tried, even if every engine still worked and every heart still longed for home. Before that point, return is merely very hard. After it, return is simply impossible, and they are committed wholly to the dark ahead. For a slow generation ship, that point arrives not as a single bright line, but as a slow certainty. Quite early in the voyage, the simple arithmetic of fuel and time closes the way back. To turn around, the ship would have to shed all its forward speed, build up speed in the other direction, and cross all the distance again, and it carries nowhere near enough fuel for that. Long before the halfway mark, turning back becomes as impossible as going on, and the only road left runs forward. But the deeper point of no return is not about fuel at all. It is about people. On a generation ship, the travellers who could have returned, the ones who actually remember Earth, grow old and die within the first decades of the trip. After that, everyone aboard was born in transit. There is no one left who has ever stood on the homeworld, no one for whom return would even be a homecoming. The very idea of going back loses its meaning, because there is no longer anyone to go back to a place they knew. This crossing is more than mechanical then. It is a passage in the heart of the whole community. There is a last person aboard who was born on Earth, who carries a living memory of its sky, its weather, its crowds and oceans. When that person dies, something final happens. Earth passes out of living memory entirely and becomes pure story, known only through records and the fading words of those now gone. The ship, from that moment, holds no one who has ever seen the world it came from. We can imagine how heavy that threshold might feel if the crew marked it at all. Perhaps the early travellers would know as they aged that they were the last who would ever truly remember home. Perhaps they would try to pass on what they could, the feel of rain, the size of the sky, the sound of a city, knowing that even their best telling would fall short. After them, those things would be only descriptions, second-hand and growing thinner with each generation, like a photograph copied too many times. For a faster ship, one that bends time, the point of no return wears a different face but is just as final. The travellers might still be alive, still the ones who left, but the world behind them would have aged past reach. Even if they could somehow turn around, the Earth they would return to would be centuries changed, peopled by strangers, their own era long buried. They could go back to the place, but never to the home, for home was a time as much as a location, and that time would be gone. Either way, the meaning is the same. Somewhere along the journey, quietly, the door behind them finishes closing. Earth becomes unreachable not only in space, but in every sense that matters. And once home is truly beyond returning to, the travellers must reckon with what home even means, when the planet that gave it that name is only a story carried in the dark. When Earth is gone beyond returning, what does the word home even mean? For the people deep in such a voyage, home is no longer a place they can go. It is a planet they have never seen, known only through old images and inherited stories, as distant and unreachable as a fairy tale. And yet it shaped everything about them, their bodies, their language, their very way of thinking. Home becomes a story they carry, rather than a ground they can stand on. For the middle and later generations of a generation ship, Earth would be wholly abstract. They would learn of blue oceans they could never swim in, of mountains and forests they could never walk, of a sky so wide it had no walls. They might see pictures and films, hear the recorded sounds of rain and birdsong and crowds. But to them these would be like images of a place in a dream, beautiful and strange, with no weight of real memory behind them. Their actual home, the only one they had ever touched, would be the ship. This raises a gentle, searching question about what home truly is. We tend to think of home as the place we come from, the soil of our birth. But for these travellers, the place of their birth is a vessel between the stars. The ship, with its curving decks and lamplit days, its familiar corridors and gardens, would be the realest place they know. In time, they might feel no homesickness for Earth at all, only a fondness, the way one feels about a grandparent's country one has never visited. There is something both sad and hopeful in this. Sad, because a profound link to the world that made us would be lost, the direct memory of Earth fading into legend within a few generations. Hopeful, because it shows how readily people can belong wherever they are. Human beings have always made homes in hard places, on ice, and in deserts, and on the open sea, and have come to love them. A ship full of people, given time, would surely come to call it home, and mean it. The new star ahead would hold a different kind of meaning, more promise than memory. It would be the destination written into every plan, the reason the voyage began, a world the earliest travellers dreamed of and the latest ones will finally reach. But for the generations in between, that star too would be abstract, a bright goal for descendants not yet born, no more touchable than the Earth behind them. They would live their whole lives between two homes, one remembered, one awaited, belonging fully to neither. So home, on such a journey, becomes something carried rather than inhabited. It lives in the language the travellers speak, the foods they grow from earthly seeds, the holidays they keep, the names they give their children, the stories they tell of where they came from. It is a home of memory and meaning, held in the mind and passed hand to hand, rather than a place with weather and a horizon. The planet recedes, but the idea of it, tended carefully, can endure. In all of this, the travellers would not be the first humans to leave a home they could never return to. Our own history holds people who set out one way, who crossed seas or wilderness with no plan or hope of coming back, and who became something new on the far side. Their stories, smaller in scale but the same in shape, are the closest mirror we have for the ones who will one day leave the Earth for good. We have done this before, in our own small way. Long before any starship, human beings set out on journeys they knew were one way, leaving homes they would never see again. The history of our species is, in part, a history of one-way travellers, of people who pushed into the unknown and never looked back, because looking back was not possible. Their stories are the nearest echo we have of the first humans to leave the Earth for good. The peopling of the Pacific is perhaps the grandest example. Over centuries, seafarers from Southeast Asia sailed out into the largest ocean on the planet, navigating by stars, swells and birds, in canoes far smaller than the emptiness around them. They crossed thousands of kilometres of open water to find specks of island they could not have known were there. Many such voyages must have ended in death, with no land found. Yet enough succeeded to settle islands scattered across a third of the globe, from Hawaii to New Zealand to remote Easter Island. Those voyagers, sailing beyond the horizon with no certainty of return, faced something close in spirit to a starship crew. They left the known world behind and committed themselves to the open emptiness, trusting their craft and their skill against a vast, indifferent space. When they reached a new island, there was often no going back across that distance, and so they stayed, built lives, and became the ancestors of new peoples. The ocean was their gulf, and the canoe their ship. The same shape appears again and again across history. People crossed the land bridge into the Americas and spread south through two empty continents, generation after generation, pressing into country no human had ever seen. Others walked out of Africa to fill the whole of the planet, each wave of travellers leaving the familiar behind for good. None of these journeys offered a return ticket. They were one way by necessity, and the travellers made their homes wherever the road finally let them stop. Even in more recent and better recorded times, the pattern held. People left old countries on ships bound for distant shores, knowing they would likely never see their birthplace or their families again. The crossing was hard and sometimes deadly, and once arrived, most could never afford to return. They carried what they could, started over among strangers, and built new lives in new lands, their old homes surviving only in letters, memory, and the stories they told their children. Many never heard from those they left again, and many were never heard from in turn, swallowed up by the distance as surely as if they had sailed into the dark between the stars. These earlier travellers did not have the physics of relativity or the dangers of cosmic radiation to contend with, and their distances, however vast they felt, were tiny beside a light year. But the human heart of the thing is the same. They face the fear of leaving everything known, the grief of permanent goodbye, the courage to step into the unknown, and the long work of making a home on the far side. In all the ways that matter to a person, they had already done what the first star travellers will do. Their example tells us something steadying. People can leave a home forever and not be broken by it. They can carry their culture, their knowledge, and their hope across a deadly gulf and plant it again in new soil. The first humans to leave the solar system would be walking a path their ancestors walked, only longer and darker, which leaves the hardest question of all still standing, the one no map or engine can answer. Knowing the cost, why would anyone choose to go? Knowing all of this, the distance, the danger, the permanence of the goodbye, why would anyone go at all? It is the honest question at the centre of this whole story, and it deserves an honest answer. There is no single reason that makes the cost worth paying. There are several, each real, and together they may be enough to send the first travellers out the one-way door, eyes open, into the dark between the stars. The oldest reason is simple curiosity, the pull to know what is out there. Human beings have always pushed past the edge of the map, not because they had to, but because they could not bear not to know. The same restlessness that drove people across oceans and into deserts, that sends us to the deepest sea and the highest peak, would send some of us to the stars. To reach another sun, to stand on a world that circles a different light, would answer a question our species has asked since the first night sky. For some, that answer alone is worth a life. A graver reason is survival. Everything that lives on Earth lives on a single world, and a single world can be lost. An asteroid strike, a nearby exploding star, a catastrophe of our own making, or simply the slow death of the sun far in the future. Any of these could end us if we remain in one place. To spread life to another star is to buy insurance against extinction, to make sure that some spark of Earth carries on even if the homeworld someday goes dark. Seen this way, the one-way voyage is not a luxury, but a hedge against the end. There is also the long horizon of the sun itself. Our star will not shine forever. In a few billion years it will swell and brighten, and the Earth will become unlivable long before that, its oceans boiled away. On a long enough view, leaving is not optional, but inevitable, if anything of us is to survive. The first travellers to another star would be the earliest step of that far longer journey, the opening of a door that our distant descendants may one day have no choice but to walk through. Beyond survival lies something harder to name, a sense of purpose and meaning. To undertake the greatest voyage in human history to carry life and mind to a new world is the kind of endeavour that can give a people a reason to strive together. It is a project larger than any one life, larger than any nation, a shared work that could outlast everyone who began it. For those who crave to be part of something vast and lasting, the building and crewing of a starship might be the most meaningful thing a person could do. And there is the plain fact that some people simply want to go. Throughout history, there have always been those willing to risk everything for a far horizon, who feel more alive at the edge of the unknown than in the safety of home. Given the chance to be among the first to leave for another star, knowing they could never return, some would still step forward gladly, drawn by the very thing that frightens others. The door that closes behind them would be, to them, a door finally open. These reasons would not move everyone, and they need not. It takes only a few, willing and able to begin. And before any of them ever leave, we have already sent something of ourselves ahead. A quiet message launched decades ago, drifting now toward the stars. We have already sent a message to the stars, and it left long ago. Bolted to the sides of the two Voyager spacecraft, the same craft that crossed the heliopause, are two identical golden records, each a kind of letter from Earth to whatever might one day find them. They were placed there in 1977, and they are still travelling outward now, the first deliberate messages from humanity launched into interstellar space. The records were the work of a small team led by the astronomer Carl Sagan. Their task was strange and beautiful, to decide what a single object should say about all of humanity and all of Earth, to a finder who might know nothing of us, not our languages, not our science, not even that we exist. They could not send words alone, since no alien would read them. So they built a record meant to be understood from first principles, a message designed to be decoded by a mind that shared nothing with us but the laws of physics. What they chose to include is a portrait of a whole world in miniature. The golden records carry sounds of Earth, the wind and the rain and the surf, the calls of birds and whales, the noises of everyday life. They carry greetings spoken in many human languages, brief hellos from across the planet. They hold music gathered from many cultures and eras, a small library of the sounds we make for beauty. And encoded in the grooves are images, more than 100 of them, showing people, places, and the basics of our science. The records were made to last almost beyond imagining. Coated in gold and built to resist the slow erosion of space, they could remain readable for hundreds of millions, even 1 billion years, far longer than the spacecraft will function, far longer than our species may endure. On their covers are etched instructions drawn in the universal language of science, showing how to play them and marking where in the galaxy and when they came from. They are a message in a bottle, cast into the largest ocean there is. The chance that anyone will ever find them is vanishingly small. The Voyagers move slowly against the immense distances between stars, and they are not aimed at any particular world. It will be tens of thousands of years before either passes anywhere near another star, and even then it will drift through empty space far from any planet. The records were never really a practical attempt at contact. They were something else, a gesture, a hope, a way of saying that we were here and that we reached outward. And perhaps that is the truest meaning of them. The golden records say more about us than about any finder. They show a species that, knowing how slim the odds, still chose to introduce itself to the universe, to gather up its music and its voices and its faces and send them into the dark with care and even tenderness. They are an act of reaching, made not in expectation of an answer, but in the simple wish to be known, to leave some trace of Earth among the stars. In that sense, the first humans to leave the solar system would not be entirely without forerunners. 2 small machines already carry our greeting outward, ahead of any crew. They are the quiet promise that we mean to follow. And if we ever do follow, if a ship full of people ever crosses that gulf and survives, then far in the future, descendants of the first travellers might arrive at last beneath a new and unfamiliar sun. Imagine, far in the future, the moment of arrival. After centuries of travel, after many generations born and buried in the dark, a ship at last draws near another star. The descendants of the first travellers, who never knew Earth and never knew the people who launched their journey, look out and see a new sun growing brighter ahead. No longer a distant point, but a true star. Their star, the end of the longest journey any humans have ever made. For them, this would be the most extraordinary sight imaginable, and yet also strangely familiar, for they would have been raised on its promise their whole lives. The new sun would swell from a bright speck into a disk, casting real light through the ship's windows for the first time in living memory. If the early studies were right, somewhere near that star would be the world their ancestors aimed for, a planet the whole voyage was meant to reach, waiting at the end of all those years. What they would find, of course, no one can say. The world might be barren, an airless ball of rock, useful only as a place to mine and build. It might be wrapped in poison air, or scoured by the flares of a restless red sun like Proxima. Or it might, against the odds, be gentle, with liquid water and a sky that could in time be made to hold a breathable air. The travellers would not know until they arrived, until their ship finally crossed the gulf and saw the new world up close with their own eyes. Whatever they found, the act of arriving would be a kind of rebirth for our species, the first time life from Earth had ever taken root around another star. If the world were kind, they might descend and begin the slow work of settling it, of turning a strange planet into a home, as their distant ancestors once turned strange islands and continents into homes. If it were harsh, they might live on in their ship, in orbit, mining the system for what they need, a human presence around a foreign sun. Either way, the gulf would have been crossed. There is a quiet wonder in picturing those arrivals. They would be human, descended from us, carrying our genes and fragments of our cultures, our music perhaps, our stories, our names, and yet they would be shaped by a world we will never see, by generations of life aboard the ship, by a journey we can only imagine. They would be our children, far removed, meeting a sky we only ever pointed at. In them, the reach that began with 2 small probes and a golden record would have touched another shore at last. And from that new shore, the old pattern might begin again. A people established at one star could, in time, look outward to the next, and send their own ships into the dark, spreading from sun to sun across unimaginable spans of time. The first crossing, the hardest and most uncertain, would have proven that it could be done. What began as a one-way leap into the unknown could become, over ages, a slow scattering of Earth's life among the stars, each world a stepping stone to the next. But all of that lies far beyond us, in a future we can only dream toward. For now, there are no starships and no colonies around other suns. There are only 2 silent probes drifting outward, a handful of bold designs on paper, and the steady pull of the question itself. We return, at the end, to where we began, to the strange and quiet truth of a door that opens only one way. We end where we began, with a door that opens only one way. At the start, we said that you can point at almost anything in the night sky and feel that, given enough time, you could go there and come back. The moon, 3 days off. Mars, a matter of months. Reachable both ways. And then everything else, the stars, lying across a gulf so wide that the journey, by the plain arithmetic of distance and speed, runs in one direction only. We have walked that whole distance now, from the edge of the sun's wind to the shore of another star. We found that the solar system does not end at the last planet but fades slowly outward, through the heliopause where the wind stops, past the long reach of gravity, to the far shell of the Oort Cloud, a journey of its own that takes our fastest craft tens of thousands of years even to clear. And beyond all that lies the true emptiness, 4¼ light years of near nothing to the nearest light, Proxima Centauri. We saw why that gulf cannot be crossed quickly. The speed of light caps every dream of a fast passage, and the rocket equation turns the carrying of fuel into a trap that defeats itself. We followed the bold attempts to beat it, the sails pushed by light, the ships driven by nuclear blasts, the fusion stars built into engines, the perfect and unreachable fuel of antimatter, and found that even at their best, stopping at the far star is as hard as the journey out, and returning harder still by far. We saw too what the crossing would ask of the travellers themselves. Either they ride near the speed of light and let time bend, returning, if they could return, to a home aged centuries past their leaving, or they go slowly in a generation ship, a sealed world carrying its people across the dark, where children are born into a voyage they never chose, where the air and water and food must cycle unbroken for lifetimes, and where home itself slowly fades from a place into a story. And through all of it ran the same quiet truth. Somewhere along the way, the door behind the travellers finishes closing. The fuel runs too low to turn back. The last person who remembers Earth grows old and dies. The signals from home stretch into years and then fall silent. Earth becomes unreachable, not only across the distance of space but across the distance of time, a world the travellers can never return to, in any sense that would let them come home. Yet we also saw that people have always done this, in their smaller way. They crossed oceans and continents one way, leaving everything known, and made new homes on the far side, carrying their songs and stories into strange new lands. The first humans to leave the solar system would be walking that same old human path, only longer and darker than any before. And we have already begun, in a way, with 2 small probes drifting outward, carrying a golden greeting towards stars they will not reach for ages. So the wonder we opened with settles into something quieter at the end. The stars are not simply far. They are far in a way that asks everything and gives no return, a one-way door into the dark. And still, knowing all of it, some of us will want to go, drawn by curiosity, by survival, by meaning, by the old pull of the horizon. The first to leave will not be coming home. They will be giving the rest of us a new one, beneath a sun we will never see.